All right, so I'm gonna start from a little bit in section 5 and work my way backwards a little bit. What I'm hoping to do here is kind of set up a reasoning for everything to work its way through. So we have what's going to be the fundamental theorem of algebra. And what this is saying is that if f of x is a polynomial of degree n, with n greater than or equal to 1, so it's not a constant, then we have at least f of x has at least one complex 0. And so this says if I'm a polynomial, I have to have a complex number that's a 0. If I cross that x-axis for any reason whatsoever, I'm going to have a 0. And if I'm a polynomial that's bent and never crossed the x-axis, I'm going to have a complex, completely imaginary set of solutions. And so this builds up with what's called the number of zeros. The number of zeros. And I've been alluding to this the whole time when I look at the power and say we have at least this many answers. I've been adding my multiplicities together to see what the strength of my function is. And so a polynomial of degree n has at the most n zeros. So a fourth degree polynomial, so 4x to the fourth plus 3x squared minus 1 equals 0, that has at the most 4 unique zeros. In fact, if we include multiplicity, if we have x plus 2 squared, and that's a degree 2 polynomial, and so it has 1 0, but it's repeated, then we can say a polynomial has n roots, including their multiplicity. Okay, so this is getting us somewhere. We can now know, looking at a polynomial, how many solutions we should see. But we run into a couple problems. Is that, well, this is saying that they're complex. And complex numbers come in our form a plus bi, where a is the real part and b is the imaginary part. And so we've been looking at, real solutions Well, we already know from quadratics there can be imaginary solutions. But when I do my polynomial, when I have a polynomial in this form, there were no imaginary coefficients. All right, we had real coefficients, real numbers for the coefficients in our polynomial. It's part of our definition of a polynomial. If we put imaginary numbers in there, we're gonna be doing different things. Algebra changes up us a little bit, but we have real numbers in there. So if we can have imaginary results, where do they go? And if we remember, every imaginary number had a conjugate, where it had the same form, but the sign was different. When we had a conjugate pair, of imaginary numbers, when I multiplied these together, I got the a squared minus b squared. It was completely real. So if I have two imaginary numbers that are conjugate pairs, their multiplication gives me something completely real. If I can have imaginary roots, but when I put their factors together such that I get my polynomial and I see no imaginary coefficients, then in all of the imaginary numbers have to come in conjugate pairs. And from this we get the conjugate zeros theorem. It's so hard saying zeros like your book does. Conjugate root theorem for me. And that says if a polynomial f of x has a zero or a root, a plus bi, then it also has a zero, a minus bi. You get the other one for free. If you have one imaginary solution, they're always going to come in pairs. Okay, so I can tell how many possible solutions I can have. I can tell that imaginaries are going to come in pairs. Well, the only other thing I need to deal with is my real numbers. And so what we can start with, okay, I have a fourth degree polynomial. I have four possible solutions. Their multiplicity and everything is in there. I'm going to have four answers. But what do those answers look like? Well, if they're imaginary, I'm going to have two of them. So what can happen with real numbers and real roots or solutions? And so what we want to do is look at the possibilities that come out of real numbers. So let's come over here. Sorry, I'm switching my screen around. I'm going to scroll down a bit here. Let's look at real numbers. And so we're going to have all these tests we're going to put together here, but they come from this idea: fourth degree polynomial, four possible solutions. Third degree polynomial, three possible solutions. Second degree polynomial, two solutions. And remember, look at what the quadratic formula did for us all the time. It gave us two solutions. Two solutions always came out of the quadratic formula. X equals negative b plus or minus b squared minus 4ac over c, or over 2a. That plus or minus guaranteed that I had two solutions coming out. And the two solutions out of this. Am I getting... There we have that there. Did I die in the water here for you? There we go. Started drawing again. All right. So we want to see what patterns we can have. So we're going to have one more test, and it's Descartes' rule of signs. And Descartes, the guy who made the Cartesian plane, he said, hey, let's talk about a polynomial, p of x, with real coefficients and a non-zero constant. And this is important. We'll show that in a second here. Writing the terms in descending powers of x. Right, which is what I've been doing the whole time, right? We've x, the highest power, down. And so what we mean by this non-zero constant. So if I have x to the third plus x squared minus x plus 0, well, we wouldn't write that 0, correct? Right, because anything plus 0 is itself. So we would write it like this. Well, I could factor out of this an x. And so this would be the polynomial Descartes' rule of sign would have to work on, is the one with the non-zero constant. Because what Descartes' rule of sign is looking for is if something is positive or negative. And this factor of x out here, or this constant of 0, is neither positive or negative. It's the boundary between it. So that's why this extra little, hey, non-zero constant has to be in this, is because we're looking at if something's positive or negative, and 0 isn't either. So we have to kind of pull out and simplify it a bit beforehand. And what we get is two things we want to check. So the first thing we want to check is the number of positive real zeros is equal to at most the number of sign variations. Or any lower number, any lower even number. So let's show this. Number of sign variations and even number of our polynomial we're looking at. So if I want to find out the number of positive real solutions, I count how many times the sign changes. So let's look at that in a number here. I'm going to, we'll go back, now we'll do this one. X to the fourth minus 6x cubed plus 8x squared plus 2x minus 1. So I start out positive and I change to negative. So that's 1. I'm negative and I change to positive. So that's 1 more. I stay positive, no change. And then I change to negative. So that's 1 more sign change. And so this is a total of 3 sign changes. So Descartes' rule of signs says I have 3 or any lower even lower by an even number, I guess would be the better way of saying it. So that means I have 3 or 2 less, 1. I count down by 2s. Count down by 2s. And so Descartes' rule of sign says this answer is going to have 3 or 1 positive real solution. All right, so I can figure out if the number's positive. Well, I guess I'm going to need to test to find out if it's negative, right? And that's the second part of Descartes' rule of signs. The number of negative real zeros is equal to, at most, or counting down by 2s, the number of sign changes in my polynomial if I put in negative for x. So let's use this one here again. But I want to put in negative x. So a negative into an even power, the sign doesn't change. A negative into an odd power, so a negative cubed is negative, a negative times a negative is positive. A negative into an even power, or 1 because I'm counting down by 2s. So at most it's 3. I have to count down by 2. So Josh asked, why is it 3 or 1 positive? So this, any lower even number, and it's counting down by 2s. So if I had 4 sign changes, I could have 4, 2, or 0. If I have 3 sign changes, I have 3 or 1. If I have 1 sign change, that's it. That's all I have. So we count down by 2s. Count down by 2s. And so if we get an odd number, we're guaranteed to have at least 1 positive real positive root. But at the most, we can have 3 of them. And we'll see how these kind of pattern together. All right, jumping back into here, I'm putting my negatives into this function. And so a negative to an even power is positive. A negative to an odd power is negative, and a negative times a negative is positive. So I'm going to put my negative into this even power. That's positive. A negative in here times this would change my sign. And this will look like this. What I tend to do is if it's an odd power, the sign changes out front. If it's an even power, the sign changes, it stays the same. And so I start out positive, I stay positive, I stay positive, I change to negative, and I stay negative. So I only have 1 sign variation. So my maximum number of negatives is 1, and I count down by 2. I can't get to 0, so I have 1 negative real solution. So I'm guaranteed 1, right? This is counting down by 2s. I can't get 2 positive real solutions. It's 3 or 1, counting down by 2s. And that counting down by 2s are those complex numbers hiding in the background because they come in pairs. If I get some grouping of these, I have to pull off pairs. And so let's look at what it means for this fourth power polynomial here. So my power, my degree is 4. My complex solutions, my positive real, and my negative reals. Now, I'm not going to look at any of the information we have here. I'm just going to start with the idea of I have to have 4 things. And so complex solutions come in conjugate pairs. So I can have 4 of them. If I have 4 of them, I have no room for any real solutions. They're all going to be complex imaginary, right? And that's my fundamental theorem of algebra, that I have 4 solutions with whatever their multiplicities are. Now they can be imaginary numbers or real numbers. Imaginary numbers come in pairs. And I cannot have more solutions than I have a degree for my polynomial. So if there are 4 imaginary solutions, I'm not going to have any reals. Well, I can have 2 complex solutions. That leaves me with 2 real solutions. So I can have 1 positive, 1 negative. I can have 2 positive, 0 negative. I can have 0 positive and 2 negative. These are all the possibilities I can have for a degree 4 function. Well, my other option is I have 0 imaginary solutions. So I can have 4 positive, 0 negative. I can have 0 positive, 4 negative. I can have 3 of these and 1 of these. I can have 2 and 2. I can have 1 and 3. And there's just every possibility I can get. If I have a degree 4 polynomial, these are my possible solutions. I can have a lot of imaginary numbers. I can have a few imaginary numbers. I can have so many positive reals and negative reals. But Descartes' rule of signs here said, hey, I definitely have 1 negative. Because this counts down by 2s, this doesn't say 0, it's 1. So I can only take the ones that have 1 negative. So I'm going to go use red here. Well, that solution set isn't possible. That one is. That solution set isn't possible. And remember, it was exactly 1 negative. And so Descartes' rules of sign says, hey, all right, you're going to solve this thing. You're trying to solve it now, and you're either going to have 1 positive real and 1 negative real and 2 imaginary solutions, or you're going to have 3 positive reals and 1 imaginary. Now notice this counting by 2. Notice here the 3 to 1, and this goes back to the question you asked, why is it 3 or 1? Has to do with the ability for there to be that imaginary conjugate pair. These have to add up to 4. And if there's an imaginary pair that takes away from it, this can't jump down to 2. It has to jump all the way down to 1. And so that's why it counts by 2. And so these things together tell us how we can find possible solutions for a problem. So let's look at bringing an equation down and finding the roots for it. And we'll start with a rational 0 and Descartes' rule of signs together. Let's see here. I'm going to use Descartes' rule of signs to see the possible reals on a couple functions, and then we'll use a couple rationals here. I have 3 examples I want to run. All right, so let's look at this polynomial here. Need a new piece of paper. So one thing about the evening class, you guys make me use a lot of chalk and a lot of paper comparatively. And I think it's because it's 2 days in one, so to speak. There we go. Back up here. All right, let me get my polynomial here. So I'm looking at 4x to the fourth. 4x to the fourth minus 5x squared minus 9. All right, and so this is a polynomial function, and we're going to look for all the zeros or solutions to it that we can find. Or we're going to try to reduce its form. We're going to try to make this tractable for ourselves here. And so we're going to want to be able to make it smaller for ourselves. And so we want to find possible roots and work our way down. Now, there's a pattern we could possibly see in this, and we can look at that pattern symbols, but let's use our rational root theorem right now. Let's look at all the possible factors of our constant. So 1 plus or minus 1, plus or minus 3, and plus or minus 9. And we'll look at all of our factors of our leading coefficient. And we get these factors from the leading coefficient. So 4x to the fourth minus 5x squared minus 9 gives us these possible factors, which means our possible solutions, our possible p over q's, are plus or minus 1. And I'm going to use each of these denominators. So plus or minus 3, plus or minus 9. Now I'm going to use this as a denominator. So I'll come down here. So I'll have 1/2. 3/2 and 9/2. And then using this as a denominator, I have 1/4, 3/4, and 9/4. No simplification helps us here, but we're in the right area. Now I can start plugging these things in for our looking for roots using the remainder theorem and test every single one of these. But what I'm going to do here is I'm going to let's see if I should focus on positive or negatives and look for things that might help pin this down. So using Descartes' rule of signs, I count my sign changes. And so I have one sign change. Right? If I count my positive, I'll use my positives in orange. Starts out positive, I change negative, I stay negative. So there's one sign change. So I have one and only one positive real. All right, well, let's put in f of negative x and look for, so I put in a negative number in here, and a negative even power is positive, even power positive. Notice my signs didn't change. So doing the negative test on Descartes' rule of signs, I have one negative real. Now these count down by twos. So I have one positive real and one negative real. But this is a degree 4. So I also have 2 imaginary results. So in looking at this, I kind of know where my answer is going. I have to get 2 imaginary numbers and 1 positive real and 1 negative real. So imaginary numbers usually come from even-powered functions. And the fact that I only have 2, I would like to get something quadratic. That would be a good goal, is to reduce this to a quadratic form. So I'm going to have to find the first root to divide through here and simplify this equation, or this polynomial. So I'm going to use my remainder theorem on each of these. And I'm going to work on the whole numbers first, because I think they go through better. So using the remainder theorem and a calculator, right? Calculators make this nice. So I'm going to show you what happens for 1 here. So 4, 1 to the 4th minus 5, 1 squared minus 9. So 4 minus 5 minus 9. So that's -1, -10. So that's not a solution. Now I want to say a little trick about this. These are all even powers. So whatever I put in for the positive one, the same thing's going to happen to the negative. Now this isn't like a rule of algebra or anything. It's just I've done enough of these that I've seen, right? -1 to the 4th is still +1. -1 squared is still +1. And so I'm going to get the same answer for these. All right, so let's put in 3. So 4 times 3 to the 4th minus 5 times 3 squared minus 9. And I'll grab my calculator over here, because this is not as easy to do in my head as the number 1 is. That's why I like checking my 1s first. Minus 5, 3 squared. Oops, let's get this downstairs. Delete, 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 delete. 4. Let's see, 4 minus 5, 3 squared minus 9. Let's see, 4, 3 to the 4th minus 5, 3 squared. That works. Let's see here. Yep. And so I get 270. Now, what's happening here is these numbers are getting bigger. And there is a sign change between -10 and 270. So I'm pretty sure if I put 5 to the 9th in. Now notice I'm not putting -3 in, because -3 is going to give me the same answer, right? So we're using our test here, and we're working our way through testing each possible number. I want to tell you right now, 9 is going to be a lot bigger than this, because our remainder changed from -10 to positive over here. We passed through 0. So somewhere between 1 and 3, we passed through 0. So somewhere between 1 and 3. Let's see what's between 1 and 3. That's not between 1 and 3. That's not between 1 and 3. That's not between 1 and 3. And that's not between 1 and 3. So we're actually looking at 3 halves. You see what's happening? Our remainder is negative for 1. When I come to 3, my remainder is positive. Somewhere in between those two numbers is 0. I've crossed 0 somewhere in there. So if I look at all of my numbers for something that's between 1 and 3, the only thing I have is 3 halves. So I'm going to jump right to 3 halves. and see what I can get from that with my remainder theorem. So I'll rewrite this in the function. Again, this is why calculators really help us out here. And I'll enter this on my calculator. So 3 divided by 2 to the 4th power minus 5. 3 divided by 2 squared minus 9 is 0. And this is my root. Well, it's my positive root, but notice, because this function was completely even, the negative is also the root. So I know my answer for this has these values. This is my exactly 1 positive real and my exactly 1 positive and my exactly 1 negative. Right? Descartes' rule of sign said, hey, you're only going to get 1 positive real and 1 negative real. And so I have 2 of my answers. The only thing I need to find now are the imaginary solutions. All right. Well, if this is one of my answers, that's the factor. And if this is my other answer, that's my other factor. So I'm going to multiply these together. X squared minus 3 halves plus 3 halves, the middle term cancels, and I get minus 9/4. That is what these two roots did. So I need to find the other factor. If I have 3 things multiplied together to get a big thing, and I want to find that third thing, I'm going to want to divide. And this is what I'm going to divide by. This is messy, but it gets us where we need to go. So 4x to the 4th minus 5x squared minus 9. That's what I need to do my division by. Now note here I'm missing terms, so I'm going to add them in as I work my way across. I have 0 x cubed terms, and I have 0 x terms. So that's what that polynomial kind of looks like underneath it all. And so I'm going to put the x squared minus 9/4 out there. All right, so x squared goes into 4x to the 4th, 4x squared times. So I'm doing my long division here. 4x squared times x squared is 4x to the 4th. And 4x squared times negative 9 over 4 is negative 9x squared. So I'm going to switch my signs and add. I get 4x squared minus 9. X squared goes into this, positive 4 times. So 4 times x squared is 4x squared. And 4 times negative 9/4 is negative 9. I switch my signs and I have 0 remainders. All right, so I'm going to do a little recap here because we're just about done with this problem. This found our solution, so let's look at it. I knew I have to have 4 answers. My rational root says if there's any rational roots, these are my possible numbers. Descartes' rule of sign says I'm only getting one positive real because there's only one sign change. So the only option I have is one real. If I put the negative in for x, there was only one sign change also. So I only have one negative real. So if I put these together, that's two real numbers. But I need four answers, which means I have to have two imaginary results. So I took my rational roots and I used my remainder theorem. Now when my remainder changed signs, I knew that I had an answer in between that sign change. And the only number I had in between that sign change was the 3/2. So I'm using all of these tests to quickly get to the, 18 possible numbers I had to check to find those two real numbers. And I found them. I found x equals 3/2 and x equals negative 3/2. But I still don't know the imaginary solutions. So I multiplied these back together to get the quadratic factor they represented, x squared minus 9/4. And I divide that quadratic factor over the initial polynomial. And that gives me this, that my entire problem, the original polynomial, could be written like this. 4x squared plus 4. Well, remember, we can always pull out the a sub n, and this has the a sub n term in it. So 4x squared plus 1 times x squared minus 9/4. But we worked out the x squared minus 9/4. Okay, so I'm using my answer here to write this in completely factored form. And so there's the a sub n hanging out front. Here's a quadratic term. And then in here are my two linear factors. And it's this quadratic term that's hiding our imaginary numbers. Because x squared plus 1, if I set that equal to 0, has x squared equal to negative 1, or x is equal to plus or minus I. And there's where my imaginary numbers were hiding. They're hiding in this quadratic term. And I wanted to use this problem as an example of what the fundamental theorem of algebra and the conjugate root theorem does, because what tends to happen is we can find these rational roots easy. The rational root test, I find people get used to plugging it into their calculator. They get the remainder theorem to pull things out. They get the rational roots out, and they're finding them fine. But what will happen is you then need to use them to reduce your problem. You need to divide this polynomial. And when you have imaginary numbers in the background, you end up with quadratics with additions in them. Because quadratics with additions in them are imaginary roots. And so we'll see this happen a lot, is we can find one or two of our rational roots using our remainder theorem, but we have to divide our problem down, so that we can get the thing that's driving the imaginary terms. And so I would say that this in general is kind of, I wouldn't say is like a worst case scenario. Is 1i squared is negative 1i squared. Yes, negative 1 is I squared. Negative 1 is I squared, yes. Wait a minute. Square root of negative 1. So Josh is asking, is negative 1 I squared? And so x is equal to plus or minus the square root of negative 1. And we call the square root of negative 1 I. And so I squared would equal -1. So if we're going backwards here and we're taking the square root of this, we have to call this I. So I think that's what you're saying is what the definition of I squared is. Yes. All right, let's look at a couple more roots, and I'm going to dive a little bit away from the more complex one. One of the things I think the book tends to do is try to find complex ones. Yeah. All right, and we're going to use some different symbolic ways to maybe make some of these easier for ourselves here. Again, we're going to try to get an idea of how many solutions we can have before we start, and then we're going to work our way through different factors. I want to pick one that works our way with a good factor. Yeah, let's look at this one. I'm going to try to find some tricks. I want to do some things that have nice tricks in them, because seeing a trick a couple times gets you out of the boat. So let's see here. We have x cubed plus 2x squared plus 4x plus 8. All right, so this has 3 as its degree. So we're going to have 3 solutions, 3 roots, 3 zeros. Now, Descartes' rule of signs, if I look at the positive version of this, there are no sign changes. Right? It's all positive. So there should be no positive roots. If I look at the negative value of it, and that's going to give me a negative there. Minus. And so if I look at this coming across, let me make sure I have this right. Negative goes into there. That's a negative. Negative of positive, negative. I start out negative. I change positive. I go back to negative. That gives me 2 sign changes. I should have 2 roots. Did I miss a sign here? Looking at my sign here. Negative x cubed. Negative 4x. So I should have 1 negative result. All right. Let's pull the real one down here. And going that we have no real zeros and 1 negative number. So 1, 2, 3, right? So this should have 3 or 1 negative solutions. Sorry, my counting was a little bit off there, and I'm like, oh, 1. Well, I shouldn't be getting 0. I should be getting 3. So there's 1 sign change, 2 sign changes, 3 sign changes. And so this is going to be 3 or 1 negative solutions. So that means my answers can be 3 negative roots and 0 imaginary. Let me make a little grid. So I have a power of 3, so everything has to add up to 3. So my imaginary comes in pairs, my positives, and my negative solutions, right? So we'll make a little chart of my possible solutions, and it has to add up to 3. But this is saying, hey, no matter what, I've got 0 positives. And I'm either going to have 1 or 3 negative. So if I have 1 negative, I have 2 imaginary. And if I have 3 negative, I have 0 everything else. And so my solutions are going to have 1 negative number and 2 imaginary numbers, or I'm going to have 3 negative numbers and nothing else. That's my solutions. And so that's what Descartes' rule of sign, the fundamental theorem of algebra, and how it relates to complex numbers lets us know what's going on here. So we know what to look for. Now, we can use our rational root theorem here. And what's really nice about this one is that my p's are going to be 1, 2, 4, and 8. All pluses or minuses. And my q's are just going to be plus or minus 1. Now, I already know I have no positive numbers. So my possible solutions, my possible roots, I'm just going to call them x twiddle because they're possible solutions. I'll put a twiddle over it. Are going to be minus 1, minus 2, minus 4, or minus 8. So I'm going to use my remainder theorem, and I'm going to test each of these out. And so what I'm going to do is I'm going to look at f minus 1, I'm going to look at f minus 2, and I'm going to look at f minus 4, and I'm going to look at f minus 8. And I'm going to run them all in on the calculator. So I'm going to just use my calculator here. I'm not going to write anything down. I'm just going to do some typing, right? And so on my calculator, I'm going to use parentheses for my function. So I'm going to use parentheses. I'm going to put a negative 1 in for x, and it's cubed. Then it's going to be plus 2 times parentheses, negative 1 in for x, and it's squared. And then it's plus 4 parentheses, negative 1 in for x, plus 8. I put that all in, and I get the number 5. So that has a remainder, so it's not a root. See how we're doing this? We're using each of these tests to look for things that we can use. All right, so I'm going to put the negative 2 in. So I'm just going to scroll up, and I'm going to copy the problem. The nice thing about my calculator is I can up arrow, and I can replace all my negative 1s with negative 2s. So I say this remainder theorem test isn't too bad with calculators now, because we don't have to write everything out. We don't even have to type everything out. We can, plop into the calculator and up arrow. I'm hopefully going to get a virtual calculator on the computer or a better camera so I can show you what I'm doing on the calculator while doing it. And so I know one of my roots is negative 2. I want to up arrow and try the negative 4. And that gives me negative 40. And I'm pretty sure I put negative 8 in. It's going to be a bigger number on the negative side too, but I'll double check here. Negative 8, negative 8, negative 8. Yeah, this gives negative 408. So I only have one negative real solution that's rational. And that's telling me x equals negative 2. So I'm going to take my initial equation and or my initial function, and I'm going to synthetically divide it with my root. Now again, because I am using the root, okay, so for row 1, why can't you have one imaginary, one real, and one negative? So imaginary numbers always come in pairs. So Josh has a question about this first row. Why can't we have one imaginary, one positive, and one negative? So when I do Descartes' rule of signs test for the positive, there are no sign changes. So there are no positive solutions. So I can't have anything for positives. This has to be 0, because Descartes' rule of sign is saying there's no sign changes on the positive version of the function. There can be no positive real roots. Now the other part of it is about imaginaries. Imaginaries always come in pairs. Because the imaginary numbers look like this, when I multiply them by their conjugate pair, I get a real answer, right? Because the middle terms cancel out. I have no i's coming into it. In all of my coefficients, none of the i's were in there. So if I had something that multiplied through there that had an imaginary, it had to be multiplied by its conjugate. It had to have its pair. It had to come in 2. And so i's always count by 2's. I's always count by 2's. Which means that these things go up and down by 2's. So if I find a total number of 4 sign changes, I'm going to have 4, 2, or 0. If I find 3 sign changes, I have 3 or 1. Those imaginary numbers in the background are coming in pairs, and so they're only letting you count by 2. Now, because this part here had 0, the positive test for Descartes' rule of signs says I'm not having any real solutions that are positive. And that limited us to these are the only 2 options. And right now it's looking like row 1 is what we have. So let me pull my coefficients here. My coefficients are 1, 2, 4, and 8. 1, 2, 4, and 8. 1, 2, 4, and 8. So using synthetic division, I'm going to bring down my 1, multiply, multiply, and the remainder is 0. And this is x squared plus 4. Oh, no problem, Josh. Imaginary numbers are weird. I introduced them back when we were doing quadratics, and I did try to warn you. They keep popping up and they hide behind things, right? They're those places where the graph turns without touching the x-axis. They turn and twist where you can't see them, and so they hide behind everything. And the best thing I can just always say is they come in pairs. They come in pairs. They're crazy that way. But if I do this synthetic division, I get a factor of x squared plus 4. And it's a positive x squared term, which you'll get used to it because you're going to do enough of these homework problems in section 4.4 and 4.5 that when you see an x squared plus a number, your brain's going, oh, that's imaginary. And so those are my factors of my polynomial. And so if I'm thinking of them as factors, I think of them as this. If I'm thinking of them as solutions, I'm saying, hey, all these things equal 0. And x equals plus or minus square root of negative 4 or plus or minus 2i. And x plus 2 equals 0, and x equals negative 2. All right, we made it an hour in on the fundamental theorem. I want to end this here. This is where I want you to start playing on the homework for sections 3 and 4. You're going to do a lot of these divisions, and you're going to start seeing these patterns. What we are going to focus on, I'm going to have quote unquote what would have been a worksheet in class that runs through do the test, get your rational roots, do Descartes' rule of signs, and plot out all the possible values of them. I'm going to do a worksheet with that. I think the best way to do that worksheet is not make it a quiz on Pearson, which is my goal, but actually make it a worksheet and send it out as a PDF. So that you can get your hands into it. You're not staring at a computer screen. You got a piece of paper. You're writing it out long form. I have the worksheet I was going to do, and what I'll do is I'll send that out in a PDF. But that will be probably with this coming Tuesday. I want to just get us. We have all of the tests now. We have our remainder theorem. which we can turn into a factor theorem. We can break things down into factors. We can divide. We can synthetically divide quickly if we need to. We have the rational root test to show us our possible rational roots. And the fundamental theorem of algebra goes, you got a fifth degree polynomial, you have 5 answers. And Descartes' rule of sign says, well, 3 of them are positive, or 1. And 1 of them is negative. And so we have these tests that help us just strip apart these really large complex things. And we keep breaking them down and breaking them down. And I want to point out, and this problem is really nice for it. At best, or at worst, we can break any polynomial down to a linear and a quadratic. Right? Any higher order polynomial, we can break down to linear and quadratic. And we've done linear and quadratic. So when we get here, we have all the tools to figure out what's going on. So anything that's higher than degree 2, we'll just beat it, and beat it with the rational root theorem. We'll hit it with our remainder theorem. We'll do everything we can. We'll divide. So that's linear and quadratic. Because we know what to do with linear and quadratic. And I've said it before. All of mathematics is taking something that you don't know what to do with, and you find some trick to make it look like something you've done before. And I've given you a whole bag of tricks right now. And what we're going to need to do is we're going to need to kick the rabbit away, because tricks are for kids. And we're going to need to play with them and get them. So I'm going to give you the worksheet that I normally would have given in class today. I'll send that out. Most likely I'll send it out Tuesday, because I'm sending everything out to all the classes at once. And I think I need like a half hour to get the other class up to that point. And so I'll send out that worksheet Tuesday. And it just practices through using all of these rules to strip down these polynomials. But I would say start practicing the homework in the books. All right. That's all I have for today. It was a long one. Those crazy imaginaries came back up. We are going to pick back up on next Thursday, or if you listen to the Tuesday morning class, we're going to pick back up from right around here. We're going to rewind about half a click, do a couple more of these things using these charts and build off on it and dive back into it. Excellent question, guys. Really excellent questions. Keeping me focused here. All right. Be safe, be well. And until again.